Okay, good afternoon, everyone. This is Anthony Robulik with the Municipal Stormwater Engineering Unit, and welcome back to Module 2 of the Stormwater Management Design Review course. We'll go ahead and get things started now. Just as a reminder to everyone that we are recording this module, as with all the modules in this course. So we ask that you please keep your microphones muted during the presentations. And if you have any questions, to please just type them into the chat, and our staff will respond. Also, as another reminder, for those of you who are interested in receiving the continuing professional competency credits or CPC credits for attending this course, they're going to be based on the hour, given that there are at least 50 minutes of instructional time within that hour. So that's going to give us 12 CPCs for this course in total. And with that, here is the agenda for Module 2. So we're going to begin the day with the presentation on stormwater calculations, and that's presented by myself. Then we'll move on to soil testing, presented by Lisa Schaefer, and that's going to be followed by a presentation from Dr. Dick McGee from NJCAT on MTDs. And after those three presentations, we'll have a quiz 2, and then we'll end the day with the quiz review. And the schedule for today usually runs a little tight, so time permitting, we'll take a quick break between presentations. So let's get started with our first presentation for today, which will cover stormwater runoff calculations. So this material is included in the course because the DP has found from previously conducted audits of the MS4 permittees that stormwater calculations are oftentimes not performed correctly. So most of you probably are familiar with these methods, as evidenced by some incorrect calculations in the project submitted for the audits. We're including this brief review in the course. Later presentations in Module 3 will highlight some of the errors more specifically, and as will the design examples in Module 4. So there are 6 major goals for this presentation, and they are: 1, understanding the Natural Resources Conservation Service, or NRCS methodology, and that's formally referred to as TR55, to calculate peak flow, volume, and runoff produced by hydrographs. Next, using the NRCS methodology to calculate runoff volume. The third goal is to calculate the time of concentration, and we'll cover some of the examples in the revised version of Chapter 5 of our BMP manual. Next, we'll take a more detailed look at hydrographs and rainfall distributions. Then we'll cover the NJDEP 2-step method for calculating runoff from an unconnected impervious area. And our last goal will cover when exfiltration may or may not be used in the stormwater routings. So first, we'll take a closer look at the NRCS methodology. So the requirement is found in the rules at the location noted at the top of the slide here, 7:8-5.7A1. And so the method listed here in the rules is the USDA Natural Resources Conservation Service, or NRCS methodology. And like I said earlier, that was additionally described in TR55. However, TR55 has been superseded by the National Engineering Handbook, or the NEH, in Part 630 hydrology. The link to that is at the bottom of the slide. So the NRCS method can provide total stormwater runoff volume, the peak flow rate, and produce hydrographs. Under the NRCS method, different synthetic rainfall distributions and different unit hydrographs can be applied to produce the stormwater runoff hydrographs in accordance with geographical differences that may affect the rainfall pattern of each storm event and the runoff pattern in a region. And that's dependent upon factors like ground slope and condition. There are plenty of software packages that use this methodology, and in later presentations, we'll cover what to check in your reviews. So the NRCS method can be used for a drainage area of any size, but the area is subject to the rule requirement that the relative stormwater runoff rates and/or volumes of pervious and impervious surfaces be separately considered to accurately compute the rates and volume of stormwater runoff from a drainage area. So the NRCS runoff equation was developed to estimate total storm runoff from total storm rainfall. The soil and cover conditions determine a parameter called the curve number, which we will discuss shortly. But first, we'll take a look at the equation that uses this parameter. So we can calculate runoff depth Q in inches by using the NRCS equation. P is our rainfall data for a particular design storm. The next parameter is the initial abstraction, I sub A, which is the stormwater volume loss before runoff begins. It includes water retained in surface depressions, water intercepted by vegetation, evaporation, and infiltration. For New Jersey, initial abstraction is equal to 2/10 the potential maximum retention S, for which we need the curve number to calculate. After determining the curve number and calculating S, we are able to calculate the total depth of runoff. So that's going to bring us to a discussion on curve numbers. So the curve number, which is abbreviated CN, is an empirical parameter used for predicting direct runoff or infiltration from rainfall excess. CN is a function of the hydrologic soil group, or HSG, and land cover, such as wood, pasture, agricultural use, but percent impervious, etc. HSGA is the most permeable group and produces the least amount of runoff when thoroughly saturated. Designations go alphabetically from B to D, with D being the least permeable group and having the highest runoff potential. The preliminary soil group classification can be found on the NRCS Web Soil Survey, but further investigation may be necessary, and Lisa will cover that next in the soil testing presentation. And she'll also go over the default HSG values one may assume. So once you have determined your HSG, or using the default assumptions that are allowed, you can determine the curve number value to input. So shown on the right is table 9.5 from the National Engineering Handbook. There are many different land uses listed here. A common land use you'll see is denoted by the arrow towards the top of the table, which is for good condition open space. Notice the CN value increases as the soil group goes from HSGA to D. So there's going to be more runoff volume for a D soil than for an A soil for a given land cover. It's crucial to use the CN value that best identifies the ground cover type and hydrologic condition. If the analysis uses pre-development CNs that are lower in value, then the analysis is considered conservative. But if the analysis uses pre-development CNs that are too high, then the analysis is considered incorrect. Note the requirement from the stormwater rules shown in the yellow box at the upper left of the slide, and that's regarding which CN values to use. This requirement also appears in the local SCO. Remember that for an impervious surface, the curve number is always 98. And lastly, note the cautionary info in the white box on the bottom left of the slide. And that means that the values in the highlighted in the red box on table 9.5 are not what you will typically see in your calculations for a development project. Okay, so what do we do when we have more than one curve number on a site? So due to the nonlinearity of the equations and losses from initial abstraction, it's important and also required in the rules to compute separately the runoff volumes from pervious and impervious areas instead of averaging the curve numbers. Particularly for the smaller, more frequent storms, averaging underestimates the volume of runoff generated by the impervious surface on a site that also contains pervious land cover. Using a composite CN value is a common error that we find in our reviews. So for example, if we analyze a site with 1 acre of impervious with a CN of 98 and 2 acres of grass lawn with a CN of 65, for the water quality design storm, using a composite CN for the site would result in roughly 70% less runoff volume than if the volumes were calculated separately for pervious and impervious areas. So using a composite CN means the BMP is likely going to be undersized for the smaller storms, including the water quality design storm. And when that happens, the BMP does not merit the pre-approved rating for TSS removal. So this is a better example from our chapter 5 in the BMP manual. So the example states a portion of a major development consists of a 200-foot wide, 25-foot long impervious surface and a 200-foot wide, 75-foot long grass lawn area that are separated by a grass swale. The soil is identified as HSGA. The 2-year design storm produces 3.5 inches of rain over 24 hours, and the slopes of the impervious surface and grass lawn are each 1%, and it's asking us to compute the volume of runoff that is produced. Just a note, this example mentions the 2-year design storm and doesn't make a distinction between the current or projected 2-year storm event. And that's because it's not really necessary for the purpose of this example, which is just to show that for a given rainfall depth, land area, slope, how different calculated runoff volumes can be with the different considerations. So from the example diagram, we see that the runoff from the impervious surface will flow directly into the grass swale. So this is a directly connected impervious surface. And when looking up the CN for the grass lawn area from table 9.5, we get a CN value of 39 for HSGA soils. And the CN for impervious cover, of course, is always 98. So next we'll calculate the volumes produced for this storm using the correct method, which is calculating pervious and impervious runoff volumes separately. And then we'll compare that with the incorrect averaging method. So using the NRCS runoff equation, we calculate S, the potential maximum retention, using our CN values and input the rainfall data to calculate the depth of runoff, which we then multiply by the area on which it falls to compute the volume. And we do this for both the pervious and the impervious areas. So for this example, the green box here shows the computation with the CN separated out, where the yellow box uses a composite CN. So if we take a look at the yellow box, we can see that averaging the CNs in this example yields a volume that is only 37% of the total volume we calculate when following the rule requirement to compute the runoff separately, which is in the green box. So calculating the runoff from the pervious and impervious surfaces separately yields a total runoff volume of 1373.3 cubic feet. And using the incorrect composite CN method, we're only getting 508 cubic feet. So this is a simple example, but it does the job to illustrate how different the results can be and why we always use the method that's identified in the green box. All right, moving on to the next goal, which will cover time of concentration. So previously we saw the definition from the rules that it is the time required for stormwater runoff to travel from the most hydraulically distant point on a site to a point of analysis. T sub C is an important parameter to get right in the calcs. So let's take a look at the next graphic to understand just why. Any site consists of one or more drainage areas, and a drainage area is a land area where all the stormwater runoff produced by that area converges to a single point. Drainage areas are sometimes called drainage basins, which are determined by the topography. They can range in size from very small up to millions of square miles. By looking at this watershed here, you'll see that due to the slopes of the area, any drop of water that falls in the valley between those two yellow shaded areas will eventually make its way to the river. And any drop of water that falls on the other side of the ridgeline will flow somewhere else, and those areas are part of a different drainage area. So something important to note is that the most hydraulically distant point doesn't necessarily mean the furthest point in distance. In this image, the surrounding terrain on each side up to the ridge lines are part of the drainage area directing runoff to the POA, which is marked by that red dot. So even though runoff has to move much further to get, say, from the mountains to the outlet of the river, the most hydraulically distant point may be somewhere else, maybe in the forest. In Module 1, we presented how various land uses, slopes, and other factors all affect how fast stormwater actually moves across the land. For example, dense vegetation like forest causes runoff to move more slowly, than the smoother land surfaces, and steeper slopes cause runoff to move faster. To compute the time of concentration, surface roughness, channel shape, and slope are the three parameters that must be characterized for each segment of flow along the flow path. Additionally, the energy level of the flow also factors into the calculation, and there are three categories to classify the type of energy, and they are sheet flow, shallow concentrated flow, or channel flow. And the two most likely to occur in site calculations are usually just the sheet flow and shallow concentrated flow. So just a little description of each sheet flow is usually at the headwaters and over plane surfaces. This is where runoff forms a thin sheet that is low in energy, also low in velocity and depth. This is what you might see on lawns or in parking lots. In Chapter 5 of the BMP manual, we note that sheet flow does not occur after 100 feet, and we'll get more into that in a couple of slides. Next is shallow concentrated flow, and that occurs where runoff begins to coalesce and pick up some more velocity. The depth is going to be greater than 1/10 of a foot, but doesn't really exhibit a defined channel yet. And then lastly, we have channel flow, and that can be seen on aerial photographs and on GIS and USGS maps. And it's essentially flow in some type of bounded channel, which is going to be higher in energy state and relatively faster than the other two types of flow. Okay, so now that we covered the types of flow energy, we can discuss the velocity method. So from the NEH, the velocity method can be used for a project site or drainage area to calculate time of concentration. So remember that the time of concentration is the sum of all the travel times, T sub T, for each type of flow in a segment along the most hydraulically distant flow path. So you can have more than one occurrence of sheet flow, for example, because maybe one of the defining parameters such as slope has changed. And this requires a calculation for each type and instance of flow over the segment or path which it occurs, and then adding them up. Just a note going forward, previously there was an assumed minimum value of 6 minutes for TC. And that was previously published in our Chapter 5 of the BMP manual, but that now must be replaced with a correct calculation. So therefore, it's important to check the reported values in your reviews. If the TC is calculated incorrectly, it could potentially impact the neighboring land infrastructure or even a local waterway. So Chapter 5 also changes the potential maximum sheet flow length, and this is in accordance with the NEH Chapter 15. So for the pre-construction condition, we assume that the sheet flow occurs for up to a maximum of 100 feet, unless there's something physically in contact with the flow of stormwater runoff, such as a swale or a curb or inlet, and that prevents the sheet flow from occurring. And it's regardless of whether the surface is impervious or pervious. If the site conditions only create, say, 75 feet of sheet flow, then just use the 75, but the max is going to be 100. So for the post-construction conditions, the maximum sheet flow length should not exceed either the McEwen-Spiess limitation or 100 feet, whichever is shorter. And the equation to calculate the McEwen-Spiess limitation is noted under the second bullet here, where L is going to be the sheet flow length. That's determined by the McEwen-Spiess limitation. S is the slope, and N is the Manning's roughness coefficient. So if the sheet flow length calculated by the McEwen-Spiess limitation criteria is less than 100 feet, then use the length determined by that calculation. But if the sheet flow length determined by the McEwen-Spiess limitation exceeds 100 feet, then the sheet flow length must be limited to 100 feet. But keep in mind this criteria is for the maximum sheet flow length that can be used. Again, if there are site conditions that have a physical obstruction at a distance that's like less than both either what the McEwen-Spiess calculates or the 100 feet, then you're going to use that shorter distance. Okay, so now that we've covered the sheet flow length limitations, we can talk a little bit about how travel time for sheet flow is calculated. So this is the travel time equation for sheet flow, which uses the Manning's kinematic equation, and listed here are the parameters which must be identified. And those parameters are the sheet flow length, which we just talked about, the Manning's roughness coefficient, the current and projected, or rather the current or projected 2-year storm event rainfall, and that's going to be depending on which storm event calculation this travel time is serving as input to. And lastly, it's going to be the slope of the hydraulic grade line. So the next couple of slides will go into a little more detail on the roughness coefficient and the 2-year rainfall depth parameters. So first, let's go over the roughness coefficient. It's also called the Manning's N value. This table here is found in Chapter 15 of the NEH. And the roughness coefficient is a measure of the roughness of a surface or a measure of the surface's resistance to flow. And there are different tables for each energy state of flow. The roughness coefficients for sheet flow are organized from smooth to rough. If, for example, a site has dense grasses, we would use a Manning's N value of 0.24. And that can be found on this table here. Note that the lower the N value, the quicker the runoff will travel. For example, from impervious surfaces, they have a roughness coefficient of 0.011. Also important is that the New Jersey BMP manual states that the maximum roughness coefficient for sheet flow in New Jersey is going to be 0.4, and that corresponds to woods with light underbrush. So we would not use a roughness coefficient in New Jersey that is greater than 0.4. That's going to be the max. So next, let's discuss the 2-year 24-hour rainfall depth parameter. If you recall, I briefly mentioned a couple slides ago that we use either the current or projected 2-year storm event rainfall depth for this parameter, and that's dependent on which storm events the sheet flow travel time is being calculated for. So when calculating the travel time for current storm events, use the precipitation depth for the current 2-year storm, which, if you remember, Peter noted in Module 1, is going to be calculated by multiplying either the NOAA Precipitation Frequency Data Server rainfall depth or the county rainfall data for the 2-year storm by the current precipitation adjustment factor for the 2-year design storm. And when calculating the travel time for the projected storm event, use the precipitation depth for the projected 2-year storm, and that's calculated by multiplying either NOAA or the county rainfall data by the future precipitation change factor for the 2-year design storm. So the P2 parameter will vary depending on whether you're calculating sheet flow travel time either for the current or projected storm events. On the slide here, you could see this is a screenshot that's taken from the NOAA Precipitation Frequency Data Server website. This one happens to be for the Trenton campus here. After navigating to NOAA, we got here by selecting New Jersey, and then precipitation depth, and then partial duration for the time series type. And you'll end up with a chart like this, but it'll extend a little further in storm duration and recurrence interval. Here you can find the column for the 2-year storm event, and then the row for the 24-hour duration. And the rainfall depth is listed here in inches. So from this chart, the 2-year 24-hour rainfall depth is going to be 3.33 inches, and that's circled in red. And you can alternatively use the county data introduced in Module 1 for this. But we're not going to be done here. So now we have to multiply this rainfall depth by either the current precipitation adjustment factor or the future precipitation change factor for the 2-year design storm, depending on whether the sheet flow travel time will be calculated for the current or projected storm events. So since the site we're looking at in this example is going to be in Trenton, we would look up the current precipitation adjustment factor and future precipitation change factor for Mercer County, which happens to be 1.01 and 1.16 respectively. And that's going to result in a P2 of 3.36 inches for current storm events and 3.86 inches for projected storm events. So that's how we calculate P2 for a site that's located within a single county, which are going to be most sites. But what do we do if we need to calculate P2 for a site that straddles a county line and there's portions of the site located in one county and then other portions of the site located in an adjacent county? So in that case, to calculate P2, we would have to first adjust each county's 2-year storm precipitation depth by either the county's respective current precipitation adjustment factor or future precipitation change factor, whichever is appropriate, and then perform an area weighted average. So as an example, if we were looking to calculate a sheet flow travel time to ultimately serve as input for modeling runoff from a current storm event, and we have a site where, say, a third of the site is located in Middlesex County and the remaining 2/3 is located in Mercer County, the first thing we would do to calculate the P2 variable is obtain the 2-year rainfall depths for each of the counties from either NOAA or the county rainfall data. So in our case, we used the county rainfall data. So these two values may be the same if you were pinpointing the site, the exact location of the site on the NOAA website, but in our case, since we're using the county rainfall data, those values are going to be different. So for the 2-year storm, that ends up being 3.35 inches in Middlesex County and 3.31 inches for Mercer County. So then we multiply those rainfall depths by each of the county's respective 2-year current precipitation adjustment factor, since they are ultimately looking to model a current storm event. But the current precipitation adjustment factor for the 2-year design storm is going to be 1 for Middlesex County and 1.01 for Mercer County. So then our final step is to perform the area weighted average. And since we have a third of the site located in Middlesex County, we would multiply that adjusted rainfall depth by 1/3. And we would do something similar for Mercer County, adjusted rainfall depth, multiplying that value by 2/3. And then summing those values together, we would get a final P2 value for current storm events of 3.35 inches. All right, next we'll cover how the travel time for shallow concentrated flow is calculated. So this travel time is equal to length for this particular segment divided by the estimated velocity multiplied by 3,600 for the conversion from seconds to hours. And velocity is estimated based on a site surface condition and slope. So the value for flow velocity can be determined from figure 15-4 of part 630 in the NEH. The velocities plotted are average values and are functions of the watercourse slope and the cover condition of the channel. So this source was derived by solving Manning's equation for a wider variety of different land covers. And on the y-axis is our slope, and the x-axis is the average velocity, and that's in feet per second. So you would draw a horizontal line from your slope on the y-axis over to the condition line, and then you draw a vertical line down to the x-axis to find what your velocity value is going to be. You may still see some citations for a TR55 source, but that's a simplified source. And remember, TR55 has been superseded, so make sure the graphical source that's used is the one here, which is in the NEH. Okay, and the last travel time we need to calculate is for open channel flow. And for this calculation, we need the length of this segment, the roughness coefficient for open channel flow, which is different from the other Manning's N value previously covered, the hydraulic radius, and the channel slope. And the Manning's N values for open channel flow can be obtained from standard hydraulics textbooks. The hydraulic radius is equal to the cross-sectional flow area divided by the wetted perimeter, and that's the surface of the channel bottom and slides that are in direct contact with the flow. Don't use this equation if you have flow under pressure, such as in a pipe. That uses a different equation. And you shouldn't see this type of flow that often in stormwater calcs for development. Okay, so now we're going to work through an example of calculating time of concentration. So this states that for a site located in Mercer County, stormwater runoff flows through a wooded drainage area along a flow path measuring 1,000 feet in length, and that's consisting of sheet flow over an area with a 0.5% slope, and then shallow concentrated flow over an area with a 1% slope. And it's asking us to calculate the time of concentration using current rainfall data. So slope of 0.5% is equal to 0.005 feet per foot. And for woods, Manning's roughness coefficient for sheet flow in NJ is going to be 0.4. The sheet flow length is calculated by using the formula for the McEwen-Speece limitation criterion, and that comes out to 17.68 feet. And since this example is using us, or is asking us to use the current rainfall data, as we previously saw, applying the 2-year design storm current precipitation adjustment factor to the 2-year 24-hour rainfall depth in NOAA results in a P2 of 3.36 inches. But actually for this, for sheet flow here in this particular site, although it wasn't mentioned in the example statement, there is actually a physical obstruction on the site that limits sheet flow length to just 15 feet. So we're not going to use the larger distance of 17.68 feet that we calculated with McEwen-Speece, and instead we're going to use this smaller distance of 15 feet, which represents the actual site conditions. So plugging all this into the equation shown is going to yield a travel time of 8 minutes for the sheet flow. So now we'll calculate the shallow concentrated flow travel time. Remember that the total flow path is going to be 1,000 feet. And since the sheet flow segment is going to be 15 feet, the length of the shallow concentrated flow is just the difference, which is going to be 985 feet. The value for the flow velocity can be determined from figure 15.4, and that was mentioned earlier. For this example, a horizontal line is projected from the y-axis to the tick mark denoting the 1% slope to the curve representing forested areas. And the corresponding velocity is going to be 0.25 feet per second. And this value is then entered into the equation for the travel time of this segment, and that comes out to be 65.5 minutes. And so our answer for time of concentration is going to be the sum of the travel times of all the segments, and that comes out to be 73.5 minutes. So next we're going to discuss developing hydrographs, and we defined those earlier as the graph depicting the flow rate of runoff versus the time passed at a specific point of analysis. A hydrograph can provide a lot of information about stormwater runoff, including the time of concentration, the time at which the peak flow occurs, the peak flow rate, and also the volume of runoff generated. So first, we should talk a little about the unitless and synthetic hydrographs for the NRCS methodology. So a unit hydrograph is a direct runoff hydrograph resulting from 1 inch of excess rainfall, and the unit hydrograph influences the shape of the runoff hydrograph, particularly the peak rate of discharge. So given a watershed's unit hydrograph, we can calculate the theoretical hydrograph for any storm event. In an ideal world, the unit hydrograph would be developed by metering the flow of a watershed. But since this isn't very practicable, we use the synthetic hydrographs instead. In general, we use 2 synthetic hydrographs, which are the Soil Conservation Service, or SCS, dimensionless unit hydrograph, and the Delmarva dimensionless unit hydrograph. And most software packages have settings that allow selection of either of these 2. So first, let's talk about the SCS, which is based on an average of natural watersheds within various sizes and geographic locations, and that allows us how to predict an unmetered watershed will react to rainfall. And it's important to note that within the state of New Jersey, the SCS unit hydrograph is used outside the coastal plain, except in rare circumstances. So shown here with an orange curve is the SCS unit hydrograph. The corresponding rainfall event is shaded in blue. As you can see, the timing of the hydrograph is based on the time of concentration of the drainage area, which is highlighted in yellow. There is some runoff at the start of the event and more runoff as areas further up gradient of the point of analysis start to contribute. The most hydraulically distant point eventually stops contributing and the runoff continues to taper off. And the volume of the runoff produced by the site in response to the rain event is going to be equal to the area under the hydrograph curve. So in development of this runoff hydrograph, the runoff discharge is nonlinear in relation to the time of the rain event in accordance with the NRCS observations from many natural unit hydrographs developed for various watersheds. The dimensionless unit hydrograph that was developed has a peak rate factor or a shape factor of 484, which means that 48.4% of the total runoff volume is discharged before the peak time, and the remaining 51.6% of the total runoff volume is going to be discharged after the peak time. And the peak rate of runoff is going to be the maximum height of the hydrograph. You can usually see the shape factor on the printouts provided in the Stormwater reports, so that's something to check in the reviews. So the second hydrograph that we're going to talk about is the Delmarva unit hydrograph. So the Delmarva hydrograph is suited for the flat coastal areas of Delaware, Maryland, Virginia, which is where it got its name. But it's also suitable for similar areas in New Jersey. So shown here is a comparison of the SCS and Delmarva unit hydrographs. When calculating the peak flow using the Delmarva hydrograph, we used a shape factor that is lower than that for the SCS unit hydrograph. The Delmarva shape factor is usually closer to 284 or 285, depending on which software you use. The Delmarva unit hydrograph will not affect the determination of runoff volume, but will result in lower peak discharges when compared to the SCS unit hydrograph. And the lower shape factor for the Delmarva means that there's less volume under the rising limb, so the hydrograph is a bit shorter in height, but it's going to be longer in duration. And this comes in part from the gentler slopes of the terrain and the lower level of urbanization and so forth. So the Delmarva hydrograph must be used in calculating pre-construction and post-construction peak flow rates for the current and projected 210 and 100-year storm events in the coastal plain region of New Jersey, and except in very specific circumstances, which we'll cover in a couple of slides. Also note that if the Delmarva is used in the precondition, it must also be used in the postcondition, likewise for the SCS. Projects which lie on or near the boundary between the Piedmont and coastal plain regions of the state should be modeled with both the standard and Delmarva unit hydrographs and results compared with actual field conditions to determine which unit hydrograph offers the best fit. So where's that boundary exactly? This is just a zoomed in view of the of a few points with a few points of interest added for the same image that was shown on the previous slide. But the blue line here is dividing the state between the coastal plain and the Piedmont region. And the hyperlink here is to the Bureau of Geologic Information Systems for the physiographic province metadata, so you can check that out. You want to be careful in outlying parts of locations near the border of the coastal plain. So for example, parts of Princeton Junction or excuse me, Princeton or Monmouth Junctions, or a little bit northwest of Trenton. The municipal stormwater management plan where the site is located may include information on this as well, so you might want to look at that. However, your best bet in determining whether a site is in the Piedmont or coastal plain regions of the state may be to use the application shown here. So this is a GIS layer noting the different physiographic provinces within the state. And this is from the DEP Bureau of GIS website. And so this allows the user to look up the actual site address to very easily make a determination as to which physiographic province the site falls in. And the link noted here at the bottom of the slide will direct you to this GIS application. So when not to use the Delmarva dimensionless unit hydrograph. So the Delmarva hydrograph must not be used outside the coastal plain of New Jersey. For another instance, use of the Delmarva unit hydrograph is not allowed when sizing a manufactured treatment device or MTD because it may underestimate the flow rates. And lastly, when a site is within the coastal plain and the design engineer can prove to the satisfaction of the review engineer that the conditions for applicability of the Delmarva hydrograph are in no way present anywhere in the watershed. For example, if the site is completely paved or there are very steep slopes present, like greater than 10% on site, then it may be more appropriate to use the SES hydrograph, but only in those cases. Okay, so in addition to the rainfall depth data, we have to know how rain falls during a storm event if we're going to create models and design BMPs to address runoff. So to estimate a rainfall event for design and planning purposes, between 1961 and 1977, the NRCS developed synthetic rainfall distributions from historical records for the different regions of the country. And the basic shape of the distributions all assume that rain starts gently and then increases in intensity towards the middle portion of the storm event and then tapers off. The type 3 distribution was previously used for about 20 years, but now we require use of the NOAA C and D distributions, and that's depending on which county we are in per the 2012 bulletin from NRCS. And a coworker here at the DEP has done some modeling using these, and we learned that you can expect to see slightly higher peak flow rates when using the C and D as compared to the type 3 distribution. So here's the map of the Northeast US depicting the regions. And the bottom left corner of the image here just shows a zoom in on New Jersey. And this figure is from Chapter 4 of the NEH, and it's also included in our Chapter 5 of the BMP manual. You can see the reddish shaded areas will use the NOAA C distribution, and the yellow shaded areas are going to use the NOAA D distribution. You should be able to download text data using this hyperlink here. And we also included a link to make this information available as an Excel file from the DEP webpage. All right, next objective. So an important approach to managing stormwater runoff is going to be the incorporation of new impervious cover that is not directly connected to a site's drainage system. So this is now extra important with the green infrastructure requirements of the stormwater rule. So to slow down runoff generated by impervious surfaces, certain key aspects must be addressed. Runoff from unconnected impervious areas must undergo sheet flow onto adjacent pervious areas, where a portion of the impervious area runoff is given an opportunity to infiltrate into the soil without causing erosion and further sediment transport to whatever's down gradient. Under certain conditions, this technique can help in providing both groundwater recharge and stormwater quality treatment for small rainfall events, as well as reduce the overall runoff volume that must be treated and controlled by a down gradient BMP. So there are 5 conditions that must be met for an impervious area to be considered as an unconnected impervious area. Here's the first 2 conditions. This basically says that the runoff must enter the pervious area as sheet flow, and it must remain that way. And the other 3 conditions ensure stability and maintain sheet flow. So for this reason, there is a limit on the steepness of the slope to 8% for the the down gradient impervious area. And there are 3 additional requirements applicable to either of the 2 calculation methods. There's going to be 2 calculation methods. Important to note here is that the minimum sheet flow length across the down gradient impervious surface must be 25 feet. All right, so like I said, there are 2 calculation methods. So the first is the NRCS composite CN with unconnected impervious from Chapter 9 of the NEH. And that's going to have that has a 30% limitation on the impervious area to the combination of the impervious surface to receiving pervious surfaces. So with that limitation met, you're free to use this method. But there's also a second method, the NJDEP 2-step method, and that's the one that we're going to take a closer look at now. So as an example of the 2-step method, we've got sheet flow over the impervious surface of 25 feet, and that doesn't exceed the maximum allowed flow path length. And we have 75 feet of sheet flow over the down gradient impervious area, which meets the minimum requirement of 25 feet. We use the NRCS runoff equation from earlier to compute the volume generated by the impervious area, which is 1362.5 cubic feet. And the next step is to assume that this runoff is evenly distributed as rain falling over the adjacent pervious surface. So to begin that step, we take a look, or we take the runoff volume produced by the design storm falling on the impervious area, in this case, the current 2-year storm event, and we divide that previously calculated volume by the area of the down gradient pervious surface to get the rainfall depth, and we convert units as necessary. We then take that rainfall depth and add it to the current 2-year storm rainfall depth, which also falls onto that pervious surface to get the total effective rainfall depth of 4.59 inches in this case. Now we can use the NRCS equation for the pervious area, inputting the total effective rainfall and the appropriate on-site retention S to get the effective depth for rain falling on the pervious area. We can then convert that effective depth to effective volume by multiplying the pervious by the pervious area. And this is going to result in a total effective volume of 156 cubic feet, and that's a pretty good reduction in volume. All right, on to our final objective for this presentation. We'll briefly go over some of the other updates to our BMP manual chapter 5. There's going to be a lot of material on these next slides, so you're going to want to read through chapter 5 on your own, as this is just going to be a brief overview. But getting into it, here are the first requirements for using exfiltration in the routing calcs, is listed on pages 7 and 8 of chapter 5. Exfiltration is only allowed for certain small-scale GI BMPs that infiltrate runoff. All soil testing must follow chapter 12 requirements, which will be further discussed in the next presentation. Also, all design criteria as provided in the respective chapter of the BMP manual must be followed before the BMP can be approved. And pretreatment must be included unless otherwise so stated in the BMP manual. An exception would be for those really small scale BMPs where the drainage areas are less than or equal to an acre. So after this, let's take a little talk a little bit about the pretreatment requirement, because that's going to extend beyond just being a requirement for using exfiltration in the routing calcs. So each of the subchapters in chapter 9 were revised. Chapter 9 of the BMP manual is now for the BMPs that are small in scale and also meet the definition of green infrastructure, because they allow stormwater to be treated through vegetation or soil, provide for reuse or infiltrate runoff into the soil. So there are BMPs in chapter 10, which are also GI, but they're larger in scale and only used to meet the stormwater runoff quantity requirement. So their use and limitations are detailed in the summary on their respective chapter cover page. They are also listed in Table 5.2 in the rules. And then finally, there are BMPs in Chapter 11, and they're not considered GI. Accordingly, pretreatment is an important design criteria. If you do not see pretreatment listed under the basic design criteria for a particular BMP, it might be under the specific design criteria. Roof runoff can be treated by certain measures listed here and on the pages listed in the bulleted text here. There are some graphics. These are taken from Chapter 9.1, and they just show a few devices that can be used to serve as pretreatment for roof runoff. So the requirement for pretreatment of roof runoff can be waived under the conditions listed here. For example, a building that is significantly taller than any surrounding trees and doesn't have a vegetative roof should not need the pretreatment. However, in making this determination, the review agency must consider the mature height of any surrounding trees. When using another BMP for pretreatment, it must be designed in accordance with the design requirements outlined in its respective BMP manual chapter. Always check the BMP manual for the specifics. Roof runoff that is commingled with surface generated runoff must be treated per the manual. For subsurface infiltration basins, as an example, pretreatment may consist of any of the BMPs found in the BMP manual, and 80% TSS removal by the pretreatment is required. Small-scale bioretention systems designed to infiltrate that have flow entering as sheet or over land flow may alternatively use a 5-foot wide gravel or stone strip to filter runoff instead of other forms of pretreatment. Those are just some specific examples. So back to the requirements for using exfiltration. Where can't you use exfiltration? So exfiltration cannot be used with any under-drained BMPs because exfiltration is removing runoff volume from the system, and under-drains don't allow for that. Also, for those sites in special areas or that have no runoff leaving the site in the pre-construction condition, exfiltration can be used for an entire storm under these conditions. You must determine which, in this case, you must determine which the maximum storm for which no runoff leaves the site in the existing condition. Another case is if infiltration of the entire storm is required by a law or rule established by either the Pinelands Commission, the Highlands Council, or other stormwater review agency that has jurisdiction over the project area. Okay, so moving on to groundwater mounding analyses. Groundwater mounding analyses are required when using exfiltration in the routings. These are the conditions that also apply. Basically, this says that soils must be tested in accordance with Chapter 12 of the BMP manual, and you must also follow Chapter 13, which is specifically about the groundwater mounding analysis method. Here are some additional things you need to know about groundwater mounding. So the groundwater mounding analysis has determined that that an adverse impact will occur if the resulting groundwater mound reaches the bottom of the BMP, or if the temporary localized increase in the water table encroaches upon a building or another structure, including any septic systems. When an adverse impact is the result, further modifications to the size of the infiltration area of the BMP or reductions in the exfiltration rate must be performed until the adverse impacts are eliminated. The groundwater mound that reaches the bottom of the BMP means that the hydraulic gradient is reduced, and that's another way of saying that the BMP cannot infiltrate runoff as fast as originally expected. So you will have to redo the routing calcs to calculate new peak flow rates. We won't run through that here, but you can refer to Chapter 5 of the BMP manual for the methodology to be used. Specifically, there's examples 5.6 and 5.7, and that begins on page 47. Groundwater mounting is itself actually a presentation in Module 3, so we'll take an in-depth look later and go through some examples then. So that concludes this presentation. If you haven't read it, again, as I mentioned, Chapter 13 includes groundwater mounting examples, so you can take a look there, and definitely check out our revised version of Chapter 5, and that also includes many design examples. Here's my contact information if you should have any questions. Thank you for your attention. Chengi, do we have any questions in the chat, or are they being taken care of?
And there are a couple of questions in the chat. First one is that a green roof would need pre-treatment for its runoff, yes, or whether treatment for its outflow. The rain on the green roof is directly on its surface, so there's no way for the pre-treatment of the rain coming to the green roof. And the runoff going through the green roof, we don't give them the runoff quality credit, so it is not considered being treated for water quality. But clean roof runoff doesn't need to subject to the TSA removal requirement. So I don't know if I answered your question.
Yeah, clean roof runoff is, sorry, I didn't mean to interject, but yeah, clean roof runoff is only going to be subject to the TSS removal rate if it ends up being ultimately commingled with surface runoff. But that would be the only case.
Yes. And the other question is that whether can you provide a link to where you can find the most up-to-date rainfall data? I don't know whether what you mean the most up-to-date rainfall data, because the rainfall data right now available from the NOAA, that was up to year 2000. So after year 2000, they did not, although they have the data from the all the weather station from this area, but they did not have any process of raw data and publish is as now you see in the NOAA's PF server. So what I can say is the most updated rainfall data is still the NOAA data that's published in the PF server. Then there was the data from most up to only to 2000, yeah. And the other one is that what pretreatment options are available yard inlets in areas of high leaf loading to protect underground detention. We have the illustration and different devices in the BMP menu. So please check it out. I can type the chapter for your reference later. And the other question is pre-treatment required if the overland runoff to the BMP is only from land grass and does not include any impervious our motor vehicle service. The pre-treatment is required for the runoff from the motor vehicle service. So if it is the clean loop runoff that doesn't have any considerable pollutant loadings, that doesn't need pre-treatment. And there's another question: if roof has to be pre-treated for leaves, then so should the adjacent lawn. Okay, so it's possible, but we are talking about the TSS, so we can consider your suggestion. Thank you. So I think that's pretty much for this presentation. So we will take a break, 10 minutes break. So we will come back and resume the presentation at 2:14-ish. Thank you.
Okay, welcome everyone back from your break. This is Lisa. I'm another member of the Municipal Stormwater Engineering Unit, and as you can guess, I'll be presenting the soil testing requirements. So we recently updated Chapter 12, so I want to make sure that you are using the March 2024 version. We updated the links and some of the content, and of course, as you can see, links change all the time, but it is our latest and greatest version. So understanding the character and saturated hydraulic conductivity of surface and subsurface soils at a proposed land development site is crucial to the design of stormwater BMPs that meet the requirements of the stormwater management rules. I'll be going over the soil testing requirements and, of course, what is to be submitted with regards to soil testing in the report for a major development project. So before I go further, I want to mention to you that it's from our audit experience, soil testing is one of those areas that we've often found has not been done correctly. So with that being said, let's move on. All right, so we will cover today the information here from Chapter 12. So that's why soil testing is needed, testing for determining the hydrologic soil group, or HSG, soil testing for infiltration type BMPs, soil testing to ascertain the location of the seasonal high water table, soil testing requirements for construction and post-construction, and what to include in a soil testing report. Now, also covered in Chapter 12 is information pertaining to testing for the input parameters in a groundwater mounding analysis. And that information you will find on page 29 of Chapter 12 and further in Chapter 13, which is what Peter will cover when he goes into groundwater mounding analyses in Module 3. So there's a misconception that soil testing is required only when an infiltration BMP is proposed. And actually, soil testing is more than just determining the saturated soil hydraulic conductivity. It also includes finding the hydrologic soil group, the seasonal high water table, and the soil series present on a site. So the identification of the correct HSG is essential to performing accurate calculations for the volume and peak flow rate of runoff, regardless of the BMP being designed. And also, BMPs require separation between the bottom of the BMP and the seasonal high water table. So for example, in a small scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the bottom of the sand layer. But for a large-scale bioretention system with an underdrain, page 11 in chapter 10.1 of the BMP manual specifies the seasonal high water table must be at least 1 foot below the bottom of the gravel layer, inside which is the underdrain pipe itself, and that sits on at least 3 inches of gravel. So if there's no soil testing report showing the depth of the seasonal high water table, you as the reviewer will not be able to judge if this design criteria has been met. So furthermore, when you're using the groundwater recharge spreadsheet to calculate annual groundwater recharge and the deficit, one needs to know not only the HSG, but also the soil series that is present. So details on this will also be presented in Module 3. And lastly, the saturated hydraulic conductivity, which generally speaking is the ability of a saturated soil to transmit water, is used in BMP design and is also needed for the input parameters in a groundwater mounding analysis. So we're going to take a look at the soil testing requirements for all of these things. So the first topic is the determination of the HSG. So that's used in your selection of the runoff curve number, or CN, for the methodology developed by the Natural Resource Conservation Service, or NRCS. So there's 3 methods used to determine HSG. One is the web soil survey. 2 is the default method, and 3 are the HSG testing procedures that are found in subsection 1C of Chapter 12 of the BMP manual. So Before we go through each of these methods, I want to touch on the subject of using those old paper versions from the county soil surveys. We checked with the NRCS and they indicated that they're no longer updating those old documents. And the NRCS further indicated that the web soil survey contains the most up-to-date information. So if you are going to use paper-backed info, you're going to have to verify it with the web soil survey. Okay, so the reason why it's on this list first is because it's the first source to be consulted for HSG information before going on and using either the second or third method. And it's very reliable, and in fact, soil maps and data exist for about 95% of the nation's counties. So the NRCS Web Soil Survey is fairly user-friendly. I think they recently updated some things, and it's really easy for you as a reviewer to check the accuracy of the submitted information. Plus, if for some reason a submittal has omitted this information, you knowing how to get to this web soil survey allows you as a reviewer to continue checking other parameters that are used in the calculations without waiting for the web soil survey information to be submitted. Okay, so to get started, once you're on the web soil survey website, just click on the green Start WSS button. After clicking the Start button, you're going to, begin with the area of interest, which is abbreviated as AOI, and that tab is there circled in red on the screen. Then you're going to zoom in to the project location using the icons in the yellow oval, or click on the address area by the green arrow and then enter the address. So then you're going to use the icons for the AOI that are shown with this turquoise oval, and you're either going to draw a rectangle or a polygon around the site. I like to check the accuracy of my polygon against the property survey to check that I got the entire area of the property. So that area information will appear under the AOI properties pull-down menu on the left of the screen above where it says Quick Navigation. So the next tab that you would click on is the Soil Data Explorer tab, which is right now it's one of those yellowy tabs or tan, depending on how you see colors. And I've added the blue oval to show you where you find it in the sequence of tabs. Next, you're going to select the brownish tab labeled Soil Properties and Qualities. It's here in the light blue oval. And then you're going to click on the pull-down menu for the item labeled Soil Qualities and Features that's located next to the green arrow that just popped up on your screen. Then scroll down to find the hydrologic soil group. That's the brownish tab shown here with this turquoise arrow. And then, by the way, I want to mention that over on the right, the orangey outlines in the soil map, okay, these puppies, okay, are the soil mapping units, and they are defined as a collection of areas defined and named the same in terms of their soil components or series, or miscellaneous areas, or both. Each map unit differs in some respect from all others in the survey area, and it's uniquely defined on the soil map. So by following all these steps, we're going to see on the next slide that by clicking on the pull-down menu for HSG will allow you to select the View Rating button right here. Okay, that's with the black oval. All right, then once you click on that, you will see a table that will appear below the map, and that will be for the soils within the AOI listed by the soil mapping unit. So that's the white area, okay? The top row in this table, I realize it could be a little hard for you to see, is Fort Mott Loamy Sand. It has a rating of A and covers the area shown on the right of the table. So here's the rating, and here's the area in your area of interest. Now, the second row is Galloway Loamy Sand, and we see a double rating in the table right here, okay? So for soils with a dual HSG rating, so that's going to be A/D, B/D, or C/D, the first letter applies to the drained condition and the second applies to the undrained condition. The appropriate choice of HSG would depend, of course, on whether or not the site has been drained. So further investigation is necessary, and we'll talk about this later. So moving down the table, we get to an area where I've superimposed this greenish gray rectangle over here, okay, on the two areas for which there's no rating. So these correspond to the two areas of the graphic inside the dashed reddish ovals that are also filled with that same grayish green. So keep in mind, when there's no rating, other steps will have to be taken. A lack of rating often happens in urban areas that have been filled with construction materials or there's some other disturbance. So when there's no HSG rating, the soils that are then undetermined for HSG, and you're going to have to go to the other two methods that I'll discuss next. And of course, those are the default method, and then those from subsection 1C in chapter 12. So one more thing I want to note is that if it is known that the site has been filled with the construction materials, debris, or something other than the soil shown in the survey map, you may not solely rely on the HSG information shown in the soil survey. You'll have to use the other methods to determine the HSG. So where HSG information from the soil survey is unavailable, default HSGs may be used for runoff computations for pre and post development conditions. So HSGs in urban areas are often unknown, and so in many instances like this, the default value can be used so that within the coastal plain, the pre-developed condition HSG to be used is that of A, and you use D for the post-developed condition. However, when you're outside the coastal plain, you use B for the pre-developed condition and D for the post-developed condition. All right, now you've seen figure 12-2 in the chapter from years past, and that's good for a general area of where the coastal plain is found, but I believe Anthony showed in the previous presentation on how to view the physiographic provinces of New Jersey on a department webpage. So here's that link again to the Bureau of GIS for their interactive website. So now you can enter a location to find out on which the province and address is located. So here's what the map on the website looks like. You know, it's zoomed out, but the page is interactive and you can zoom in enough to differentiate between two houses on a street. Okay, see the outlines of the properties. And I'm pointing to here 401 East State Street, all right, right next to that green arrow where that dot is, okay? And we see that that is in the Piedmont province. The lighter blue area on the bottom of the screen, this down here, okay, is the coastal plain. And so now I think you'll appreciate how much easier it is to figure out if you're in the coastal plain. Now, one other thing I want to mention is that for the groundwater recharge spreadsheet, table 12-2 in the chapter has been updated to show default soil series for recharge computations. This table is on page 6 of the chapter, and there's a discussion on page 10 of the chapter, and we'll also include this further in module 3. All right, so if you don't want to use the HSG values, then you go to the soil testing. You will have to do soil testing to ascertain the HSG. All right, so the third solid bullet is a quote from chapter 7 of the NRCS National Engineering Handbook. All right, the web link may be out of date. All right, but regardless, chapter 7 states that the assignment of HSG is determined by the water transmitting soil layer with the lowest saturated hydraulic conductivity and depth to any layer that is more or less water impermeable, such as fragipan or durapan, or depth to a water table if present. The least transmissive layer can be any soil horizon that transmits water at a slower rate relative to those horizons above or below it. Okay, so we're going to go and move on to table 7-1 from, I believe it's still on page 112 in chapter 7. And this table relates saturated hydraulic conductivity to the hydrologic soil group. All right, so this is table 7-1 from the NEH. And again, we look at the depth to a water impermeable soil layer that has a saturated hydraulic conductivity of 0.0014 inches per hour or less. We look at the depth to the seasonal high water table, and then the saturated hydraulic conductivity of the most restrictive soil layer within the depth to a water impermeable layer. Okay, so I'm going to read you this quote from chapter 7, which says certain wet soils are placed in group D based solely on the presence of a water table within 24 inches of the surface, even though the saturated hydraulic conductivity may be favorable for water transmission. So if these soils can be adequately drained, then they're assigned to dual hydrologic soil groups, A, D, B/D, and C/D, based on their saturated hydraulic conductivity and the water table depth when drained. The first letter applies to the drain condition and the second to the undrained condition. For the purpose of hydrologic soil group, adequately drained means that the seasonal high water table is kept at least 24 inches below the surface in a soil where it would be higher in a natural state. The HSG designation is in the right-hand column. All right, so if the depth is less than 20 inches, the soil is classified as D per the top row in the table. Now, where the depth to the water impermeable layer is between 20 and 40 inches, we look in the area of the red oval. Okay, then if the depth to the high water table is less than 24 inches, we would look at the rows to the right of the orange label, meaning this part. Okay, so this is where we find the appropriate saturated hydraulic conductivity range for the least transmissive layer within the corresponding depth range for the site conditions. Now, of course, just a short while ago, we learned that the link has changed since we made the slides. So it's here, and I believe someone may be able to put that into the chat, okay? But we'll be updating this for future use. Moving on, we're going to continue with the testing procedures. Okay, so the presence and depth of the restrictions must be included in the soil logs for each soil profile pit and boring. So on the left, we see a soil sample log showing the depth to the restrictive layer, and the seasonal high water table is shown here in blue. Now, on the right is a shallow soil pit with a face that's been cleaned and prepped for describing the soil profile. So this one happens to be from Alaska, and this one's only 15 inches deep, which is the depth of the permafrost. Okay, anyway, we're going to look now at the required number of the soil profile pits and soil borings that are required for soil testing that is performed to determine the hydrologic soil group. Okay, so for each soil mapping unit less than 0.5 acres, 1 pit and 1 boring are required. For each soil mapping unit between 0.5 and 2 acres, 1 pit and 4 borings are required. And for each soil mapping unit greater than 2 acres, 1 pit plus 1 pit per each additional 2 acres, and 4 borings plus 2 more borings per each additional 2 acres are required. So the placement of soil profile pits and soil borings is also an important part of the requirement. They should be completed equidistant apart within the boundaries of the mapping unit to provide adequate characterization. So we're going to look at 2 examples. One for the pink area, which is 2 acres in size, we see 1 soil profile pit and 4 borings. So this configuration meets the placement area. Okay, For the 6-acre area on the right, that's the green shaded 3 segments, okay, we see 3 pits and 8 borings. That's 1 soil profile pit and 4 borings for the first 2 acres, then 1 soil profile pit and 2 borings for each additional 2-acre segment. So this configuration also meets the placement requirement. Now, there's also a depth requirement in the determination of hydrologic soil groups. All right, in the previous version of the chapter, when it was Appendix E, you needed a depth of 6 feet. Okay, but now Chapter 12 requires at least 40 inches. Okay, so the presence and depths of soil classification must be included in the soil logs. Okay, so this represents the end of the soil testing requirements for determining hydrologic soil group. Okay. Oh, but there's also an updated workbook for soil testing for you to download from our website. All right, I want you to make sure that you check the date of the update in the bottom right-hand corner. These are the March 2024 websites, okay? And so what this means is that if you are seeing tan or orange filled cells, that's the older version of the workbook. Green and yellow is the new set of colors. All right, and shown here is the first worksheet, which is also figure 12-3 in the chapter, okay? In the top part, you enter the size of each mapping unit, and the spreadsheet calculates the number of soil profile pits and also the number of soil borings required. The results are then displayed in the columns that are filled with the yellow color. And then the lower part of the worksheet can be used to calculate the depth of a soil profile pit or boring. So based on the information that you enter, in the event that the soil seasonal high water table is within 24 inches, a message will be displayed indicating that there are HSGD soils. Okay, so that represents the end of HSG soil testing. Okay, next are the soil testing requirements for infiltration BMPs, and that's found in section 2 of chapter 12. First of all, by infiltration BMPs, we mean those that infiltrate runoff into subsoils, including the BMPs such as infiltration basins, of course, along with sand filters, bioretention basins, and pervious paving systems designed without underdrains. Testing for BMPs with underdrains is separate and will be discussed a little later. So let's first look at the number of soil profile pits and soil boring requirements for any infiltration BMP. Okay, so we need to know where the seasonal high water table is located. So a minimum of 2 soil profile pits must be excavated within the infiltration area of any proposed infiltration BMP to determine the elevation of the seasonal high water table and to test the hydraulic conductivity of the most restrictive horizon between the basin bottom and the seasonal high water table. Placement, meaning left to right on the site in plan view, all right, of the test pits must be sufficient to provide adequate characterization of the infiltration area. And for those BMP infiltration areas that are larger than 10,000 square feet, a minimum of 1 additional soil profile pit must be conducted for each additional area of 10,000 square feet. Now, at least 1 test to establish the soil hydraulic conductivity must be conducted for each soil profile pit. So when reviewing the plan, in order to verify the locations and numbers of the soil profile pits, you'll need to see a site plan depicting those locations to make sure they are within the infiltration area of the proposed BMPs. Okay, now, substitution and proximity information are also found on page 17 of chapter 12. All right, a soil profile pit may be substituted by soil borings only when the conditions stated in the subsection that has the title Soil Boring and Profile Pit Locations and Allowable Substitutions, which begins on page 7, are fully met. the final location of a proposed BMP can differ from the location of a soil exploration. All right, but this is important. As long as the proposed BMP is within the same soil mapping unit, a new soil exploration is not required under the following circumstances. So if the soil explorations that have been performed are still within the infiltration area of the BMP at its new location, and also if the new location of the BMP is within 25 feet in any direction of all of the original soil exploration locations. All right, so let's do an example of determining the number of soil profile pits needed for an infiltration BMP with a bottom area measuring 100 feet by 250 feet, which gives us an area of 25,000 square feet. So for this infiltration basin, we would need 2 profile pits for the first 10,000 square feet, which since the basin is 100 feet wide translates to 100 feet of length. As marked here, and 1 for the additional 10,000 square feet in the middle, plus 1 more for that extra 5,000 square feet on the right end. Okay, so the next few slides are going to look at the number and location of tests for special types of infiltration BMPs. And that is going to include small scale and then linear BMPs. And then after that, we're going to go on to the other tests we need to perform for all BMPs designed to infiltrate. Okay, so for our small scale infiltration BMPs, when we have one or more, multiple, of the small ones. All right, we're going to need 1 soil profile pit for each soil mapping unit where the multiple BMPs are located, plus for each BMP with an infiltration area less than or equal to 500 square feet, we're going to need 1 soil boring at each BMP. For each BMP with an infiltration area greater than 500 square feet, you're going to need 2 soil borings at each BMP. And for small scale GI BMPs that are arranged linearly, you're going to need 1 soil boring at each BMP and then 1 soil profile pit for every 2,000 feet along the length of the linear arrangement. Okay, so this information is written out on pages 15 and 16 of the updated chapter 12. Okay, so let's move on to linear infiltration BMPs. And by that, all right, all 3 of the bulleted criteria must be met. And this information you'll find on page 15 of chapter 12. So for linear infiltration BMPs, a minimum of 1 soil profile pit must be conducted within each soil mapping unit. In each soil mapping unit, the soil profile pit must be conducted within the first 500 linear feet of the BMP. And where the length of the linear BMP exceeds 500 linear feet, then 1 soil boring must be conducted at every 500-foot interval, and 1 additional soil profile pit must be conducted for every 2,000 linear feet. All soil explorations must be equidistant to adequately characterize the infiltration area. So let's do some examples for linear infiltration BMPs. And we have 2 sites. The first one is shown on the top of the slide, and it has 2 soil mapping units. Okay, one is yellow, one is green. So we must include 1 pit for a linear BMP 500 feet in length, shown in the yellow area. And then we need 1 pit for the first 500 linear feet of the soil mapping unit that's shaded in green. Okay. And then with 1 boring for each additional 500 linear foot portion. So as long as 2 pits and 3 borings are performed, this example would meet the requirements. For the second example, there's a linear infiltration BMP with a total length of 2,500 feet, and it's all within 1 soil mapping unit. So what's needed is the required pit for the first 500 linear feet, followed by one boring for each additional 500-foot increment, and then one more pit for the additional 2,000 linear feet after the first 500 feet covered by the initial pit. Okay, these examples are figure 12-4 in chapter 12 of the BMP manual. I always go back and check them every time I'm reviewing something. Okay, so let's move on to the other soil tests needed for infiltration BMPs, which are those to determine the soil hydraulic conductivity, and that depends on whether or not we are proposing soil replacement. So for the scenario in which no soil replacement is proposed, after determining the numbers and locations of the soil profile pit for the infiltration BMPs, you're going to have to decide the depth of the soil profile pit. Okay, and then there's the question of which soil layer to select for performing the test for soil hydraulic conductivity. So soil hydraulic conductivity testing must be conducted on the most hydraulically restrictive horizon or substratum above the seasonal high water table or non-fractured bedrock, but located below the lowest elevation of the BMP and above whichever of the following depths is greater. Excuse me, 1 second. 8 feet below the lowest elevation of the BMP, or to a depth equal to twice the maximum potential water depth in the BMP measured from the lowest elevation of the BMP. Okay, and so from our audit experience, the depth to which the soil exploration extends to locate the most hydraulically restrictive layer is quite often inadequate. That can greatly affect the performance of your BMP designed to infiltrate. Now, if soil replacement is proposed beyond the required layers in the BMP, the depth is measured from the elevation of the bottom of the required sand or soil layer, the stuff you're putting in to replace soil. Okay, this requirement means first that the excavation of the soil profile must reach to the required depth, and second, the hydraulic conductivity must be tested on the most hydraulically restrictive soil layer below the soil replacement or lowest part of the point of the basin, but above the required soil profile depth. So note that the depth requirement of whichever is greater, 8 feet or twice the maximum water depth, is measured from the lowest point of the basin bottom or from the bottom of the soil replacement, whichever is deeper into the earth. Very often, we've seen that the soil hydraulic conductivity test is performed at the top of the soils to be replaced, but doesn't include the depth of the replacement, and that is the wrong place to do this testing. Okay, so up next is a discussion of what test methods are acceptable for this type of soil testing. Okay, soil hydraulic conductivity can be determined using a tube permeameter, a percolation test, a single ring infiltration test, a basin flooding test, or a modified basin flooding test. You're going to have to read the specific conditions that are published in Chapter 12 under which each of these tests can be used. Now, additional methods of establishing the soil hydraulic conductivity, such as ASTM D3385, the double ring infiltrometer, and USBR 7300-89, the well permeameter method, or other soil hydraulic conductivity tests that utilize in situ conditions and are accompanied by a recognized published source reference can be used, such as the Guelph permeameter or the Philip Dunn permeameter, which is available at Soil Science Society of America in book series 5, Methods of Soil Analysis, Part 1, under the area of Physical and Mineralogical Methods, written by Clute, which dates back to 1986. So when performing a soil boring and during the soil exploration, the soil borings must be performed and reported in accordance with ASTM D1452, Practice for Soil Investigation and Sampling Auger Borings, and ASTM D1586 test method for penetration test and split barrel sampling of soils. Sampling must be continuous for the entire depth of the soil boring to fully characterize the soil profile. So since the actual saturated hydraulic conductivity rate may vary from soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated hydraulic conductivity rate to determine the design saturated hydraulic conductivity rate, which is what is then used to compute a BMP's drain time for the maximum design volume. Also for the exfiltration rate for a BMP allowed to use exfiltration in the routing calculation, or the recharge rate in the groundwater mounting analysis. Now, where any tested saturated hydraulic conductivity rate is 20 inches per hour or more, the maximum design saturated hydraulic conductivity rate that can be used is 10 inches per hour. So the test procedures and conversion equations for the test shown here are available in Chapter 12. And there's also worksheets for some of these, okay? You can see everything here in subsection A1 for perk tests, A2 for 2 permeameter tests, then there's the basin flooding test, the modified basin flooding test, and the single ring infiltration test, each of which begin on the pages shown here. Okay, now, at some point, the case borehole infiltration test was suspended for further assessment. And what's new is that the ASTM's standard for this test indicates that it's not suitable for cohesionless soils. So upon closer review, the soils for which the test could be appropriate are those which would have saturated hydraulic conductivity ratings below the minimum for an infiltration BMP. So that is why the case borehole test is removed from Chapter 12. So for double ring infiltrometer, well permeameter, and other permitted testing methods, you're going to obtain them from the American Society for Testing and Materials or whatever organization published the test method. So for the PERC test, you're going to follow the procedures described in Chapter 12, and the field measured hydraulic conductivity value will be calculated using this simplified equation, and this is also in Chapter 12. But I want you to take note that the test step 4B in the procedures that's described, all right, it requires the tester to fill the water to a depth of 7 inches, but the time of recording is started when the water level drops to 6 inches. And then it stopped completely when the water in the hole is emptied. If I said stopped, I meant started when the water level drops to 6 inches and then stop when the water is gone. So the second worksheet in the Excel workbook may be helpful for hydraulic conductivity testing. On the left is the top and the middle portion, and of course the right is on is the bottom portion. All right, and that's for the depth of testing. Now, I want you to take note that the title has changed as well as the fill colors. All right, and there's a reason for that. I'll get to that in a minute. All right, so all right, next we have to do this, the testing to determine the seasonal high water table. All right, you'll see it abbreviated throughout here as SHWT. So pursuant to table 5-1 in the stormwater management rules, this testing is not applicable to BMPs such as blue and green roofs, as they're constructed as above grade BMPs, plus the others where no separation is listed in this particular table. All right, the testing to determine the location of the seasonal high water table is required for those BMPs with underdrains, for grass swales, and of course, BMPs designed to infiltrate. This section of the chapter never stated that underdrain BMPs were excluded. So that's why we're clarifying this issue. Okay, so for BMPs that are designed to infiltrate, you're going to follow the guidance for determining the saturated hydraulic conductivity, and you're going to make sure that you test at least 2 areas within the footprint, meaning the bottom area where the infiltration will actually take place. Now, for non-infiltration BMPs, you're going to test within the area to be occupied by the BMP, and then follow the number of tests required, like those for infiltration BMPs, based on area and so forth, okay? So if you're getting inconsistent results in your tests, or you see, as a reviewer, inconsistencies, all right, then you're either going to perform or require more testing, as the case may be. Now, I've also prepared a graphic that's going to illustrate when certain testing and resource data may be used for determining seasonal high water table. All right, and this table should clarify some misunderstandings about when to perform soil testing, okay? I want you to take note that the subsection 1D in the chapter has been updated to further clarify this issue. So when you set out to determine the location of the seasonal high water table, there's a sharp divide in how you determine where it's located, and this is based on your observations. That is, the features you see depending on the time of year the exploration is made. And so the next few slides are going to fill in the details from this graphic, and this is all found beginning in chapter 12 with page 11. All right, so let's start with the simple case, meaning what applies when the answer to the question of whether modeling is observed is yes. Okay, so let's focus on this. So at any season of the year where modeling shows redoxamorphic features, or where modeling showing redoxamorphic features is observed, the seasonal high water table shall be taken as the highest level at which the redoxamorphic features are observed, except where the water table is observed at a higher level than the level of the redoxamorphic depletions or concentrations. Okay, so for details on determining whether saturated soils are present, the guidance document published by NRCS called Field Indicators of Hydric Soils in the United States may be used. So where modeling showing redoxamorphic features is not observed, the seasonal high water table shall be determined as followed, where A corresponds to the yellow shaded arrow and B corresponds to the arrow with the red fill. Okay, so during the months of January through April inclusive, water levels may be measured directly within the soil profile pits or borings. Of course, whenever the department determines that there's been a significant departure from normal climatic conditions, the department may, with due notice to the administrative authority, lengthen or shorten the period allowed for direct measurement during any given year. In low-lying coastal areas where groundwater levels fluctuate with the tides, measurements shall be taken at the time of highest groundwater elevation in response to tidal fluctuation. But take note, there's been no such change in the time frame for direct observation. Okay. During other times of year, all right, the depth to the seasonal high water table is obtained from the NRCS Web Soil Survey, provided that the soil series present at the site is identified based upon comparison of soil profile morphology observed within a soil profile pit and the soil profile description provided for the soil series in question within the NRCS Web Soil Survey. So in cases where the seasonal high water table is shown as a range of elevations in the NRCS Web Soil Survey, the highest elevation of the range is what is used as the seasonal high water table. Okay, so this is the complete graphic for your use. Now, so if you're performing your exploration in August and a feature such as modeling is observed and it's showing redoxamorphic features, okay, that's where the seasonal high water table shall be marked as located unless the water table is higher than them. All right, but I'm sorry, it should say April. But if you're doing testing outside of January through April, if you don't see modeling that indicates redoxamorphic features, then you're going to follow the text that's cited in the stormwater management rules in 5.82E. Okay. All right, so for those of you who prefer text over graphics, tables 12-5 and 12-6 in the chapter are going to be your source for guidance on seasonal high water table determination, all right, depending on observations and the time of year. So 12-5 corresponds with item 1 in the citation, and that's on page 12 of chapter 12. All right, and table 12-6 is for the item 2 under the citation. Okay, so it's very descriptive. Okay, I think you'll find it much better and much more clear. All right, so on page 26 of the new chapter 12, figure 12-8 depicts the top part of the Excel spreadsheet created to serve as your template for a soil profile report. The workbook, including the spreadsheet, of course, is part of the set that can be downloaded from the department website. All right, and so it's very helpful for recording your observations. All right, next, we're going to move on to the construction and post-construction oversight testing requirements. So during construction, regular oversight must be provided by the professional engineer to establish the basin will function as designed. Oversight includes, but is not limited to, the following. So a pre-construction meeting with the contractor, confirmation of the proper use of construction equipment, especially to minimize the compaction of the infiltration area, ensuring that the earthwork does not occur within the BMP area when the soil moisture content is above the lower plastic limit, and that the specifications of any replacement soils is or are met. Ensuring that proper precautions are taken to prevent sediment entering the infiltration area during construction, or where unavoidable, if the basin is to be used as a sedimentation basin, excavation for the sediment basin is at least 2 feet above the final design elevation of the basin bottom. So post-construction soil hydraulic conductivity tests must be conducted to ensure that the BMP that has been installed functions as designed. And this is part of the design criteria in many subchapters of the BMP manual. Such testing must be carefully undertaken when all BMP construction that may affect soil hydraulic conductivity has been completed. This includes the use of all construction equipment and the placement of all construction material that may affect hydraulic conductivity. In addition, hand tools and manual permeability test procedures must be used to avoid affecting soil hydraulic conductivity. So the required number of tests for post-construction testing are as follows. So you must follow the same requirements as those for pre-construction soil hydraulic conductivity tests. And as for the required depth, okay, the post-construction hydraulic conductivity test must be conducted at the bottom of the excavation of the BMP before the sand layer or soil bed is placed into the BMP. The permitted test methods for post-construction soil testing are as follows. Only the single ring infiltration test, the modified basin flooding test, and the double ring infiltration test or similar test that does not require a test hole in the soil layer are allowed. The tested soil hydraulic conductivity from the post-construction hydraulic conductivity test must be equal or greater than the tested soil hydraulic conductivity of the most restrictive soil layer that was tested in the pre-construction condition. And lastly, all post-construction soil hydraulic conductivity tests must be certified by a licensed professional engineer, submitted to the review agency, and then recorded in the as-built documents. All right, so far I've covered the requirements for soil testing that will provide information on the hydrologic soil group that determine the runoff from the site, for the saturated hydraulic conductivity that determines the permeability of the soil underneath the basin, and for the seasonal high water table that determines if the BMP can be drained at all. So I hope you understand that soil testing requirements are essential to proper stormwater management design. So since exfiltration is allowed in routing calculations for infiltration BMPs, the volume and flow rate of runoff that can be actually infiltrated into the subsoil will affect the sizing of the BMP and outlet structures. So more than ever, soil testing results that correctly describe the soil characteristics are very important. All right, so this is what should be submitted within the stormwater management report, and the reviewer should check that all of the following or all the information shown on this slide is included. Okay, so that's just about everything I have for today. So just to recap, we covered the information all from Chapter 12. So it's why we need soil testing, HSG determination testing, soil testing for infiltration BMPs and for non-infiltration BMPs, testing to locate the seasonal high water table, and what the requirements are for construction and post-construction soil testing. And lastly, what information should be included in the soil testing report. As a reviewer, it's important to check each and every part of the information submitted for accuracy, since this greatly influences or determines how well your BMP is going to function. So the design example in Module 4 will probably, will still include these checks. All right, so you can reach out if you have more questions to me or to the unit email address. All right, and at this point, I'm going to ask Chengi if there are any further questions. If you'd rather, you can send them also by email.
We don't have further question. All question in the chat is being answered.
Great.
So yeah, so we will move on,
on.
and yes, please invite Dr. McGee to give us his presentation. Thank you.
Thank you. All right, Dr. McGee, is your microphone on? Because I don't hear you. So up next will be Dr. McGee from the New Jersey Corporation for Advanced Technology, and he's going to discuss the NJCAT DEP partnership for the verification and certification of manufactured treatment devices. Dr. McGee, are you there?
Is it on now?
Yes, it is. Okay,
All right.
so are we ready
just
to
had
go?
I had to find the right button. It's different today.
I know, they keep moving it around. You all set?
Okay, I'm all
All
set. Hello, everybody. I welcome you and happy to be here today. I'm here to talk about the Stormwater Manufactured Treatment Device, or the MTD Verification Certification Program. There are 6 areas that I hope to cover. A brief history of the establishment of NJCAT, that's New Jersey Corporation for Advanced Technology, and our working relationship with DEP, the role of MTDs in meeting the requirements of NJAC 7.8, the specific NJCAT verification program. I want to show you 4 examples of NJCAT verified, DEP certified MTD technologies, just to give you an idea of the innovation and the breadth of technologies that are in this program. Then I want to focus some significant time on the misuse of certifications outside NJDEP, and also things that you have to be concerned about misuse of certifications inside DEP. And then finally, some idea of the status of the program and where we are moving forward. Next slide. Just some history. The history here began back in the late 1990s, and where the state legislature decided that's the public interest to encourage new businesses to locate in New Jersey and assist existing enterprises to remain and expand in the state by facilitating the development and commercial use of technology-based environmental and energy-related products. It came out of some discussions between then Commissioner Robert Shin, former Governor Jim Florio, and Stevens Institute of Technology President Hal Ravichet. The 208 legislature, which ran from July 1, 1999 to 2000, established a technology verification program under Senate Bill number 1750. and they implemented $95,000 to initiate the program. Since this appropriation, we've received no money from the state, but the program has been sustained by fees from the manufacturers to NJCAT to administer the program. Next slide. Key to the program was the Energy and Environmental Technology Verification, EETV Act, which was approved on January 18, year 2000. And it really outlined the roles and responsibilities of the state of New Jersey, NJDEP, and NJCAT. By the way, NJCAT was established in 1998. Next slide. Critical to this whole program was a performance partnership agreement, which was adopted in June 6th, year 2000. And hence, our partnership between NJCAT and DEP has been active for over 20 years. In fact, shortly next year, it'll be 25 years. Key elements of this partnership is that NJDEP is required to consult and work with NJCAT to develop performance evaluation and verification procedures, processes, and protocols, and to determine the application and use of certain IEETS, okay, innovative environmental energy technologies. To date, NJCAT has focused predominantly on stormwater MTDs, but has also verified the performance of remediation technologies, heavy metals removal from drinking water, field analytical methods, and combined heat and power systems, to name a few. Excitingly, just recently in November 2023, less than 6 months ago, an MOU was signed between DEP and NJDBPU to enable NJCAT and NJDEP to work with a BPU to achieve the state's greenhouse gas emissions reduction goals. The initial focus of this partnership will be on ground source heat pump HVAC systems. Next slide. In Module 1, the history and federal acts predating the post-construction stormwater management program and MS4 permit requirements were presented, and they're just highlighted here on this slide. You've already seen this. Next slide. Next slide. Okay. We're going to now focus on manufactured treatment devices. So the question is, what is an MTD? A manufactured treatment devices are a subset of BMP. So therefore, they're in the BMP manual. They're proprietary, prefabricated stormwater treatment systems that rely upon a variety of mechanisms to remove pollutants from stormwater runoff. The mechanism they use are settling, filtration, organic, inorganic media, vortex separation, vegetative components, other appropriate technology to remove pollutants from stormwater. I said settling in the beginning. That was probably more settling that would be related to Stokes' law settling, so to speak. Okay, next slide. All right. As you know, your stormwater management rules require all projects to remove 80% of the project's TSS runoff on an annual basis. You'll also know that NJAC 7.8 requires the use of green infrastructure BMPs that manage stormwater closely to a source by, and there are several categories: treating stormwater runoff through infiltration into the subsoil, or treating stormwater runoff through filtration by vegetation or soil. We will spend more time on that as we go through the presentation later on. NJAC, provides approved TSS removal rates for both BMPs and MTDs. It's our job then to do the verification of these MTDs to give you a removal rate to use in your calculations. And finally, the key to the whole program is removal rates for manufactured treatment devices are we verify, i.e. verified by NJCAT, and they are certified by NJDEP. So this is a true partnership. And as I've said previously, these our verifications have to verify against the protocols and procedures that have been established by DEP. Next slide. Okay, now we're going to get into the verification program. We conduct an independent third-party evaluation program to verify the performance claims of innovative environmental energy technologies. I think we should all be proud of the fact that the program has strong national and international recognition. I'm constantly talking to other countries, currently now Australia, New Zealand, and Germany, that want to bring their technologies into the program to be verified and certified, which gives them not only the ability then to market in the States, but also gives them international recognition in Canada and these other countries as well. The system has, as I say, evaluates against DEP test protocols, and it's important to recognize that these test protocols were reissued in 2021 and 2022 to reflect lessons learned since the first test protocols were issued in 2013. And as we go through, I want to point that out because that's important for you as you're looking at technologies that may be being offered for a particular project. The hydrodynamic sedimentation MTDs will only give you 50%. And sedimentation means either just pure gravity separation via Stokes law, or it can be vortex separation, as you'll see in some of the devices I talk about. Those protocols were updated January 1, 2021, and then slightly updated in 2023 to reflect more stringent requirements on laboratories doing the analysis. Filtration MTDs have to adhere, they give you 80% removal, and those protocols were updated in 2022, issued in 2022, reissued, and then listed in 2023. Currently over 50 MTDs have been NJCAT verified and NJDEP certified. Okay. But importantly, 13 of them have already been sunset. And the reason they've been sunset is that hydrodynamic separators, and we'll talk more as we go along, that were verified and certified under the old approaches, under the old protocols, we felt had learned how to play a game and how to I would call, jump the test, so to speak, by depositing sediment in the inlet pipe, and we're not a true indicator of how the BTM BTD actually was operating. So currently there are 12 hydrodynamic separators that are verified certified. Importantly, 7 of these have sunset dates this year and 1 next year. So they'll be down to 4, which means there's a lot of activity coming in right now. Many of the companies that will no longer be able to do business in New Jersey have innovated their technologies. The new designs coming in are not the same as the old designs that were verified and certified well over a decade ago. And I think that's going to improve the overall process. Filtration devices, there are 14, and point out that the filtration devices have no sunset because the protocol between 2013 and 2022 did not change significantly enough that there was felt that there was a need to require retesting. And then, interestingly enough and excitingly, green infrastructure is the new growing category of MTDs, and that is determined by DEP. And what I mean by determined by DEP is they're certified, verified against a filtration protocol right now, and then they're certified by DEP. This is the fastest growing area of MTD verification certification program in the program. Interestingly enough, since the year 2020, we've been adding about 2 GIs, into green infrastructure technologies, into the program each year. Next slide. Okay, now I just want to quickly run through some of the technologies that you might see. You may not be that interested, but they show you some idea of the innovation and the thought process. Because this is called a debris separating baffle box. Inlet, it's piped in from the inlet pipe on the right-hand side. It's got a set of screens on the top. I'll show you another view of this. Thank you, Lisa. And there are 3 sediment chambers below, okay, where the sediment is collected. And then it goes out the other side. It also has an oil skimmer and hydrocarbon boom, which are optional at the other end. Next slide, which gives you a vertical view of it. Now looking down on the system, the stormwater comes in from the left. There's a flow splitter, which separates the flow into 2 areas. Because the screen on the front only clean debris, clean stormwater with debris free goes through the center where a gravity settling takes place. The stormwater which runs off to the left or the right also has screens which says that the sediment will settle down below and everything is collected, and then everything is at the outside. Now, what is important to this technology is obviously if the inlet and the outlet are not on the same line, if you call coming in on the horizontal line there, right, then this technology is not going to work. And I have not seen any yet, but I have seen some cases where the manufacturers have offered technologies with different inlet outlet pipes or orientations, and they obviously were not tested that way, and the performance cannot be taken that way. Now, the last point I'll tell you about this one, this technology is going to sunset in June next month, and I don't know if they're going to come back in and get it recertified, but there is a new technology, another manufacturer with a very similar technology, which has its technology out for public comment. And let me just tell you what public comment means. Any technology that goes through the verification program has to be offered to public comment, which generally means the other manufacturers, for review, and all their comments must be satisfied before I can sign off that the report verification report meets the standard and pass it on NJDEP. And that technology right now is in the in the public review process, and comments are being resolved and addressed on that technology. So this one will no longer be available, but one very similar will be available, I expect, within a week or two from my end. Okay, let's go on to the next slide. Now, I told you that was simple gravity separation. This one is in a manhole. Again, coming from the inlet pipe, there's a flow splitter. We'll see that in a different diagram. There's also an oil floatable skimmer as well. And basically, you can see the fluid's going to come in. It's going to go down below that oil floatable skimmer. That's where the sump is. Comes back up the other side. There's pipes which allow you to drain down and then back at the other side. All right, next slide. This gives you a view looking down into the manhole. You'll see the flow coming in from the left. It hits the deflector plate. The way to design up, it creates two rotating vortices behind that plate, which then increases the time and settling for the sediment. It will go down underneath, which you have to go back to the other one to do underneath that center skimmer, back up the other side, and then it goes out the pipe. Again, you notice these pipes are in line. This technology would not work, certainly not work the way it was tested if, say, for example, that inlet pipe was, say, 10 or 20 degrees off the center line exactly, either way. And therefore, you have to be very careful because I've seen too many plans that come in with people offering technologies that are not with this technology per se, but were not the way they were tested. All right, let's now go on and take a look at the next one. I'd say there's a lot of filters. Filters are interesting. Filters can be downflow filters. They can be upflow filters. They can be canister or cartridge filters. And a lot of different neat ideas that people are coming in. This is the case of a cartridge filter. You see a cartridge chamber. It was tested with two cartridge filters in the chamber. The inlet pipe comes in. There is some settling in the inlet chamber. Also trapping floatables behind the floatables baffle. And then eventually it goes in and it fills up at the bottom, the chamber with the cartridges, and then the cartridges treat radially into that center pipe, and then there's an outlet pipe on the outlet side. Key to all types of filters is maintaining the proper scaling ratios, because if you think about it, in this case here, you're getting sedimentation and removal both in that inlet chamber as well as stuff that is going to settle out on the floor of the cartridge chamber, and then the fines are going to be removed in the actual cartridge filter itself. Interesting, most of these devices are designed so that probably 85 or 90% settles out on the floor, and only the polishing occurs through the actual filter itself. If not, you would be plugging your filter up too quickly and you'd have a maintenance problem. Next slide. Here's another case of a filter, but it's a filter that becomes a GI. You see here, fluids coming in, say, off of a curb inlet, goes into a device there which has got soil inside, percolates down through the soil. You can then have a planting in the device there. That's what kind of makes it green through the soil, down into the outlet chamber after you have filtered water, and then it goes out the back end. All right. So this is a case that DEP has determined as a GI, green infrastructure, because ultimately it's being treated by soil. The other two categories I mentioned previously, it could be treated by vegetation. These, by the way, this one here is never tested by vegetation because it takes too long to establish the plant growth. But in any event, if the soil can treat it, then the assumption is even with a planter in there, with the additional activity that goes on, it would also. And but in this one here, since it's very hard to infiltrate the entire amount into the subsurface, and you just had a tutorial on that, all of the material here then goes out into a storm drain or something. A variation of this in the next slide. It's the last show and tell I have for you. Same company, Contech, has now developed a canister filter, which is from a soil media. The stormwater comes in, it fills up the chamber. The water then radially goes through that cartridge and to a center line, goes out and then into a under drain manifold into an outlet on the other side. So there are lots of things that you may see, different devices in your plan reviews. All right, now let's get to a very important topic, which is the next slide, which is misuse of the certifications. First bullet, not all NJCAT verified stormwater technologies are NJDEP certified. And this is confusing to, I don't think you in New Jersey, but to a lot of other states which rely on this program, because I get calls from regulators all the time. Well, what does it mean to only be NJCAT verified and not NJDEP certified? And what it simply means is they did not test exactly to the NJDEP protocol. And the biggest area is they want to test for a larger D50 sediment. The sediment that's specified by New Jersey has a D50 of 75 microns, which means 50% of the sediment is below 75 microns, 50% is higher. Some states say, well, wait a minute, I don't want to put in a filter. What particle size can you remove and get, say, for example, 80% removal rate? In many cases, that is going to be a sediment that has a D50, probably about 110 or 120 microns, quite a bit coarser than that. And there's a market for that. So some technologies have, in fact, been tested both against the New Jersey test sediment as well as the more coarse sediment. Currently 32%, which is 12 of the currently certified storm are GI certified. If it's GI certified, that means it has met the test protocol for 80% removal filtration test protocol, and it has been deemed to fit the GI definition as given by DEP. This is the big one, the third bullet. Only the HDS MTD configuration that was tested has been DEP certified. Manufacturers will frequently offer other configurations claiming certification. They are not certified. And the three that you have to worry about is inlet outlet configurations that is not 180 degrees apart. We tried to point to that with Lisa's help. Some want to use multiple inlet pipes. They'll have two inlet pipes coming into the device, which is not tested. And on occasion, I have seen people try to put in grate inlets, which means it's a straight drop down into the device, not in the outlet. So you want to be very careful about that. Generally, I get these called to my attention by competing manufacturers who realize that people have submitted plans and are offering their technology to New Jersey. I then contact the department. People write a letter, and I think that this gets pulled off. But those are three biggies. Watch them. There is now the opportunity to test not 180 degrees apart. The new protocol allows it. Only one manufacturer has tried to do it, and they were not successful. But there may be more coming in. But right now, there are none that any of those three sub-bullets would have been certified for. And then for reviewers, it's imperative to check that the configuration shown on the plans matches the configuration tested as noted in the NJDP certification letter and illustrated in the NJCAT verification report. So that's a key slide, okay, because that'll help you do your job. All right. Next slide points out that the two things. One is your regs say an MTD cannot be used in series with another MTD or a media filter, such as sand filter, to achieve an enhanced removal rate. You probably know that. But MTD certified for offline use cannot be used in online configurations. And that's always part of the certification letter from the department. Obviously, if it's been certified for online, it can be used for offline. And I've had that question asked to me because the whole idea of online and offline depends upon worrying about scour. You don't want to put a system in an MTD where if you exceed the flow rate at which it was certified, say by 200%, for example, for HDS, that you're going to scour out all the sediment that you already collected. So for an HDS system to be online, it has to show that it does not scour out collected sediment, and there's a criteria for that. Rarely the filters try to get online installation because the filters are typically designed to treat lower flow rates to get the 80% removal rate. So it's rare. I can only think of one technology that actually demonstrated that they could be online for a filter, and that was for a specific flow rate. All right, next slide. Okay, the program continues to evolve, okay, which is exciting. If you go to our website, you'll see that we've expanded the database and we've added explanatory text, and because to help confusion to those who don't work with this program every day. So we list stormwater technologies that have been laboratory verified and NJDP certified. We've broken them down into 3 subcategories with supporting text. We've tried to explain why some technologies are only laboratory verified. I told you the most critical example there is the D50. Some technologies might only be in public review. I think right now there's one in public review. Probably next week there'll be another one in public review, which says that they've gone through the verification process. Now it's being opened up for the public and other manufacturers to challenge if there's anything they feel is inappropriate. Sometimes things get by even NJCAT, and it's generally wording. Manufacturers try to make claims that we're really not part of the verification process. We think we're pretty good at screening them out, but not always. And then there's the additional energy environmental technologies that I talked about before. Finally, there's a second page, so to speak, of archive reports. And because the program has changed so much over the years, and because we have new protocols, as I already mentioned to you, many of the technologies are no longer recognized in New Jersey, but the industry asked if we couldn't at least archive them. So since they did go through a testing process, and they could make reference to them. So there are 3 subcategories here. For your viewpoint, nothing in these categories could be utilized in New Jersey. Next slide. Program moving forward. Obviously, we're managing the implementation of the new HDS protocol. No longer will manufacturers get credit for sediment deposit in the pipe. It's only that which is captured and removed in the device itself. There are currently 7 technologies certified under the old protocol, which were required to undergo retesting by 12/31/24, or they'll drop off. Many of these will elect not to retest and move on to improved designs. One HDS technology, due to the quirk and how we set up the sunset time, will go to the 5th of June in 2025. And there's a lot of activity now going on in hydrodynamic separator technology development by the manufacturers. ASTM has got involved, American Society of Testing Materials. They've established an E64. They're developing test protocols now, standard on the NJDEP laboratory test protocols. They're also going to do one for field testing. Currently, 3 HDS MTDs that are verified only will be sunset by December 2024, because they were testing as the old protocol. If they want to come in, for example, with a larger D50 and still be verified, they can, but they're going to have to do it against the new protocol. I don't know how much there is. And then finally, there's a new program called the STEP Initiative, Stormwater Testing and Evaluation for Product and Practices. This is an initiative by the manufacturers. It's heavily driven by the manufacturers. If you are not willing to pay dues to them, you don't get to vote. I think they hope to take over this whole program nationally. And I will be watching it, not because I'm trying to maintain the NJDEP program, but I'm a little concerned that the manufacturers are more interested in their profit margin than they are in other things. And if I have to be quoted on that, yes, I will be quoted on it, because I already told them that. And they don't have a very robust evaluation and program like we do, so that NJCAT doesn't foul up. And so I think there's going to be a lot of things that get done under the radar. But hopefully they'll get their act together, and then maybe NJDEP, NJCAT can sunset this program as well. I think, next slide. I think that we got to the question time, and I think we got to it in time, Lisa. So I think I met my criteria. So happy to answer any questions anybody has.
Changi, do we have any questions?
No. I think
Wow.
Dr. McGee has explained the program very well. Thank you, Dr. McGee, and we will work together.
Well, we've worked together for
Thank you.
many years, and I'm happy to participate in this effort.
Thank you.
Thank you.
Okay, good luck on
Thank
your
you.
quiz, guys.
Oh yeah, so speaking of a quiz, all right, it's time for quiz 2. So now one thing we did not cover today is how to size MTDs for use to address the water quality requirement. Changi will cover that in Module 3 as part of how to review a project under Part 2, and that will also be covered in the rule amendments presentation in Module 4. So Peter is going to take us away with the quiz, and followed by the review. And of course, we're going to give you the QR code in the chat momentarily if you want to use your smartphone, or like I told you at the beginning, you'll be given instructions on how to open the quiz in a new window or tab so that you're not booted from the training. All right, so please stand by while I hand control over to Peter.
Okay, thank you, Lisa. Yeah, so as Lisa said, we're going to get into quiz number 2 now. As noted before, it's important to complete the quiz now during the time allotted. Note that you can't move forward to complete a quiz or complete a quiz at a later time, and we need the quizzes to be complete in order to issue credit for the class. Okay. All right, so just like Tuesday, as Lisa was describing, we have a few different ways to get to the quiz. You can use the handouts link in the middle of the page here and scroll to the bottom of that web page that it leads you to and click on the link for quiz 2. You can also use the SurveyMonkey link at the bottom of this slide, which will also be posted in the chat, and that'll take you directly to the SurveyMonkey quiz. And then lastly, you can use the QR code. You can scan that with your smartphone to be taken to the quiz to do it on your phone. All right. And yeah, just a few other quick notes. You must answer every question on the quiz before you can advance to the next screen and finally submit. You may only take the quiz once, and we're a little tight for time here, so we're going to allow 10 minutes for people to take the quiz. So we will give until 3:55. And yeah, if you finish early, you could feel free to take a short break. And then after that time, we will review the answers to each question from the quiz. And the review portion of the quiz is part of the course and for credit and attendance. So please do not leave after completing the quiz. All right, so here's everything all in one place, and you may begin taking the quiz. Thank you. All right, welcome back, everyone. So we are aware that not everyone might be finished the quiz yet, but you can feel free to continue working on the quiz as we go through the review, but we are going to get started on it since we're tight for time here, and we might not go through each question in detail. So if you do have any questions on a specific question in the quiz, you can feel free to email us or send a message in the chat, and we'll get to those questions. All right. So we'll start at number 4, true or false. There's no longer a minimum or default value that can be used for time of concentration using the NRCS methodology, meaning this value must always be calculated. And that is true. All right, number 5, according to the NJ Stormwater BMP manual, what is the maximum roughness coefficient that can be used in sheet flow calculations for wooded conditions in New Jersey? And the correct answer for this one is 0.4. Number 6, what is the maximum sheet flow length for the pre-construction condition, assuming there is no physical constraint present to prevent sheet flow from occurring? And 100 feet is the correct answer. All right, number 7, according to the stormwater management rules effective on July 17, 2023, which methodology can be used in the computation of stormwater runoff? And the correct answer is the NRCS method. Number 8, true or false, when using the NRCS methodology for directly connected impervious cover, averaging pervious and impervious curve numbers is permitted for calculating a hydrograph. And that is false. Number 9, when determining the curve numbers for site design, the design engineer should assume that the condition of the existing cover is good condition. That's the right answer. Number 10, yes or no, can the Delmarva dimensionless unit hydrograph be used for the redevelopment of a 2-acre entirely impervious site located within the coastal plain? And the answer to that is no. Number 11, true or false, when using the NRCS methodology for calculation of stormwater runoff, type 3 rainfall distribution must be used for developments in New Jersey. And that statement is false. Question 12, true or false, pre-treatment must be incorporated into the design of a small-scale GIBMP that has a drainage area greater than 1 acre, infiltrates runoff into the subsoil, and uses exfiltration in the routing calculations. And that is true. Number 13, soil testing logs prepared in accordance with Chapter 12 are required for which of the following BMPs? And the correct answer is all of the above. Number 14, true or false, a factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate, which is used for infiltration BMP calculations. And that is true. Number 15, yes or no, during the month of July, can the seasonal high water table be determined by measuring water levels directly within a soil exploration if the modeling does not indicate redoxymorphic features are present within the soil exploration? And the answer to that is no. Number 16, when is it necessary for the design engineer to assess the hydraulic impact on the groundwater table? And the correct answer is whenever an infiltration BMP is proposed. Number 17, how many soil profile pits and or soil borings must be performed for 5 small-scale bioretention basins and 1 mapping unit that are each 450 square feet and scattered around a development? The correct answer is 1 soil profile pit for the soil mapping unit and 1 soil boring for each small-scale bioretention basin. Okay, question 18, true or false? In a small-scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the surface of the sand layer. And that is false. Number 19, where on the soil horizon should soil permeability tests be performed when no soil replacement is proposed? And the answer is to perform the test on the most hydraulically restrictive soil layer below the BMP and above the seasonal high water table or bedrock to the greater of 8 feet below the lowest point of the basin or 2 times the maximum potential water depth. And then number 20, the last question, true or false? When choosing a hydrodynamic separator type MTD, the inlet configuration, such as the angle and number of inflow pipes, must strictly match the inlet configuration described in the NJCAT verification report. And that is true. All right, so that is the end of the quiz review, and that's the end of Module 2. So the next session, Module 3, will be this Tuesday, May 7th. And I want to thank everyone for their attendance and participation, and I will hand it over to Changyi to conclude the module.
We know we have the very short time for the quiz, so if you have not finished the quiz, please finish and submit it. The submission of your quiz is part of our counting of the attendance. So we must receive your quiz. We will open the quiz up to 4:15. So please finish it and submit it before you leave. If you already finished and submit the quiz, you may leave now. And thank you for everyone's participation of today's training. Thank you very much.